Right now, as you lie here, something extraordinary is about to begin inside your skull. A hidden drainage system is opening its gates, flooding your brain with cerebrospinal fluid, literally washing away the molecular debris of everything you worried about today, everything that exhausted you, everything you no longer need. You are not simply falling asleep. You are entering the most sophisticated self-repair sequence known to science. And tonight, you are going to travel through 100 quiet revelations about the architecture of your own mind, 100 truths about how your brain dissolves old wiring and builds new pathways while your body lies perfectly still. You will learn how neurons reach out like pale branches in the dark, searching for each other, forming connections that did not exist when you woke up this morning. You will discover how the glymphatic system opens channels between your cells, flushing the proteins that cloud your thinking, restoring clarity you forgot you once had. You will understand how your brain quietly unlearns the anxiety it practiced all day, softening the neural circuits of fear simply because your conscious mind has finally stepped aside. Think of what follows as a neural restoration session. Each fact is a pulse of healing. Each sentence builds a new connection, not only in your understanding, but physically, inside the living tissue behind your closed eyes. 100 steps through the biological architecture of the mind that is listening to these words right now. And if you feel yourself drifting, let it happen. Do not resist. Your brain absorbs these truths more deeply when your waking mind is out of the way. Sleep is not the enemy of learning. Sleep is where learning is completed. So settle in. Let your breathing slow. The journey through your own extraordinary biology begins now. For most of the 20th century, the scientific world believed something about your brain that turned out to be profoundly wrong. Researchers, doctors, and textbooks all agreed that the adult brain was essentially fixed, a finished product that could only decline with age. Once you passed childhood, the story went. Your neural architecture was set in stone. No new cells, no new connections, only a slow and inevitable erosion. This belief shaped medicine, psychology, and even the way people understood themselves. If the brain could not change, then neither could you. But as you lie here tonight, breathing slowly, letting your muscles soften into the surface beneath you, know this: that old story has been completely rewritten. Your brain is not a monument. It is a living garden, and it has been quietly reshaping itself since the moment you were born. The discovery that overturned everything arrived not in a single dramatic moment, but through decades of quiet, persistent observation. Scientists studying patients who had suffered strokes noticed something that should have been impossible. Regions of the brain that had been damaged were somehow transferring their functions to healthy neighboring tissue. The brain was not passively accepting its injuries. It was routing around them, finding new pathways, reassigning responsibilities, as if it contained an invisible architect who refused to accept limitations. This phenomenon was eventually given a name that would reshape our understanding of what it means to be human: neuroplasticity. The brain's lifelong ability to reorganize itself, to form new connections, to dissolve old ones, and to physically rebuild its own structure in response to experience, environment, and even thought itself. At the very foundation of this extraordinary ability lies a structure so small that millions of them could fit on the head of a pin: the synapse. This is the microscopic gap between two nerve cells where one neuron reaches out to communicate with another. When you learn something new, when you recall a memory, when you feel an emotion wash through your body, it is because electrical signals are leaping across these tiny gaps, carried by chemical messengers called neurotransmitters. Tonight, as your brain begins its transition into sleep, trillions of these synaptic conversations are still murmuring beneath your awareness. Some are strengthening, some are fading. The balance between those two processes is one of the great mysteries of how you become who you are. Picture, if you can, a single neuron deep inside your brain. From its cell body extend long, branching filaments called dendrites, and they look remarkably like the branches of a winter tree reaching into fog. These dendrites are not static, they are searchers. Throughout your life, they extend and retract, growing toward other neurons, probing the darkness for new partners with whom to form connections. When a dendrite finds another neuron that is firing at the same time, something beautiful happens. A new synapse is born, a new pathway opens. A thought that was once impossible becomes possible. This is happening inside you right now. Even as you listen to these words, your dendrites are reaching outward like slow vines in a garden that never stops growing, even in the deepest hours of the night. One of the most astonishing revelations in modern neuroscience is that your brain does not merely rewire its existing cells, it grows entirely new ones. For decades, this was considered impossible, a heresy against established science. But researchers eventually confirmed that in a region called the hippocampus, buried deep in the temporal lobe, fresh neurons are born throughout your adult life in a process called neurogenesis. These infant neurons migrate to their positions, extend their dendrites, and integrate themselves into existing networks. They are especially important for learning and memory. And here is the part that matters most tonight. Sleep is one of the most powerful triggers of neurogenesis. As your body rests and your breathing deepens, your hippocampus is quietly producing the building blocks of tomorrow's thoughts and memories. The hippocampus itself deserves a moment of quiet admiration. Shaped like a tiny seahorse curled inside each hemisphere of your brain, this ancient structure is the gateway through which new experiences must pass before they can become lasting memories. It is the librarian of your life, sorting through the day's events, deciding what to keep and what to let dissolve. During sleep, the hippocampus replays the day's experiences at accelerated speed, sending them outward to the cortex for long-term storage. This is not a metaphor. Electrodes placed in the hippocampi of sleeping animals have recorded the exact same firing patterns that occurred during waking experience, played back like a song the brain is memorizing by repeating it in the dark. There is a substance wrapped around many of your neural fibers that transforms the speed and efficiency of your thoughts, and it carries a name that sounds almost gentle: myelin. This fatty white sheath spirals around the long axons that connect one neuron to another, insulating them the way rubber insulates an electrical wire. Without myelin, a neural signal that should arrive in milliseconds would stagger and dissipate before reaching its destination. With myelin, that same signal travels up to 100 times faster. When you practice a skill repeatedly, whether it is playing an instrument, speaking a language, or simply navigating a familiar route home, your brain responds by wrapping additional layers of myelin around the circuits involved. You are literally paving the roads of your own mind, making the pathways smoother and faster with every repetition. Myelination is not confined to childhood. While it is true that the most dramatic period of myelination occurs in the first years of life, when the brain is building its fundamental architecture at breathtaking speed, the process continues well into adulthood. Every time you commit to learning something deeply, every time you return to a practice with patience and repetition, oligodendrocytes, the specialized cells responsible for producing myelin, wrap another layer of insulation around the relevant fibers. This is why mastery feels different from mere familiarity. A master has not simply memorized a set of facts. A master has physically insulated the neural highways that carry those facts until the signals travel so quickly and so smoothly that the knowledge feels less like thought and more like instinct. Now consider what happens to the connections your brain no longer needs. Just as a gardener must prune dead branches to allow new growth, your brain engages in a process called synaptic pruning. Throughout your life, but especially during sleep, your brain evaluates which connections have been used recently and which have been neglected. The neglected ones are quietly dissolved. Their raw materials are recycled and redirected toward connections that are actively being strengthened. This may sound like loss, but it is the opposite. Pruning is how your brain maintains clarity. Without it, every neural pathway you ever formed would persist, creating a dense, tangled thicket of competing signals. Pruning is the brain's way of saying that letting go is not a failure. It is an essential act of intelligent design. The nightly pruning cycle is governed in part by a principle so elegant that it has become one of the most quoted ideas in all of neuroscience. In 1949, a Canadian psychologist named Donald Hebb proposed a simple rule: neurons that fire together wire together. This means that when two neurons are activated at the same time, the connection between them grows stronger, and the reverse is equally true. Neurons that fall out of synchrony gradually lose their bond. This principle, known as Hebbian learning, is the foundation upon which your habits, your memories, and your personality are physically constructed. Every repeated thought etches itself more deeply into your neural tissue. Every abandoned pattern slowly fades. You are, in the most literal sense, sculpted by what you choose to practice. Hebbian plasticity operates on a scale that is both humbling and empowering. Consider a fear you once had that no longer troubles you. Perhaps as a child you were afraid of the dark, or of a sound, or of being alone. That fear was once a robust neural circuit, reinforced every time you experienced the stimulus and responded with anxiety. But over time, as you encountered the same situation without the expected harm, the circuit weakened. The neurons that once fired together in panic gradually fell out of rhythm. The synapses thinned. The fear did not vanish because you decided to be brave. It vanished because your brain, following Hebb's rule, physically dismantled the wiring that sustained it. Courage, it turns out, is a form of neural architecture. While you sleep, your brain enters a state that scientists call offline processing, and it is during this time that some of the most important plastic changes occur. Free from the constant demands of sensory input and conscious decision-making, the sleeping brain can devote its full resources to consolidation. The process of transforming fragile new memories into stable, long-lasting ones. Short-term traces held in the hippocampus are replayed and gradually transferred to the neocortex, where they are woven into the broader tapestry of your knowledge. This transfer does not happen during a single night. It unfolds across many nights, each sleep cycle adding another layer of stability, another coat of myelin, another round of pruning that sharpens the signal and quiets the noise. Deep within the architecture of sleep itself, there is a phase called slow-wave sleep, and it is during this phase that your brain performs its most profound restorative work. Slow-wave sleep is characterized by long, rolling electrical oscillations that sweep across the cortex like tides moving through a calm ocean. These slow oscillations synchronize vast populations of neurons, allowing them to fire together in coordinated rhythms that strengthen the connections between them. It is as if the brain is conducting an orchestra in the dark, bringing every section into harmony. The deeper you descend into slow-wave sleep tonight, the more thoroughly your brain will consolidate what you have learned, reinforce what matters, and quietly release what no longer serves you. There is another phase of sleep that plays a different but equally vital role in neuroplasticity, and that is the phase of rapid eye movement, or REM sleep. During REM, your brain becomes intensely active, almost as active as when you are awake, yet your body remains in a state of near total paralysis. This is when dreams emerge, those strange, vivid narratives that seem to follow no logic. But beneath the surreal surface, your brain is performing critical work. REM sleep is when emotional memories are reprocessed, when the sharp edges of distressing experiences are softened, and when creative connections between seemingly unrelated ideas are formed. Many of history's greatest insights have arrived not through effort, but through the quiet alchemy of REM sleep. The relationship between sleep and emotional regulation is one of the most important discoveries in modern neuroscience. When you are sleep deprived, the amygdala, the brain's threat detection center, becomes hyperactive. It begins to interpret neutral stimuli as dangerous, flooding your system with stress hormones and reactive impulses. But after a full night of sleep, particularly one rich in REM cycles, the prefrontal cortex reasserts its calming influence over the amygdala. The neural balance between fear and reason is restored. This is not a metaphor for emotional healing. It is the physical mechanism by which emotional healing occurs. Every night that you sleep well, your brain is literally rewiring the circuits that govern how you feel about your life. Consider now the role of a molecule called brain-derived neurotrophic factor, often shortened to BDNF. This protein acts like a fertilizer for your neurons. It supports the survival of existing nerve cells, encourages the growth of new ones, and strengthens the synaptic connections that form the basis of learning and memory. BDNF levels rise during sleep, particularly during the deep, restorative phases. When you wake feeling mentally clear and emotionally grounded, it is in part because your brain spent the night bathing its circuits in this growth-promoting substance. Think of BDNF as the rain that falls on the garden of your mind while you are dreaming, nourishing every root and stem without your conscious knowledge. Your brain consumes roughly 20% of your body's total energy, despite accounting for only about 2% of your body weight. This extraordinary metabolic demand produces waste, just as any engine produces exhaust. During waking hours, these metabolic byproducts accumulate in the spaces between your neurons, gradually clouding the efficiency of your thinking. But during sleep, something remarkable happens. The glial cells that surround your neurons shrink by as much as 60%, opening wide channels through which cerebrospinal fluid can flow. This is the glymphatic system, the brain's dedicated waste removal network, and it operates almost exclusively during sleep. Right now, as your body settles deeper into stillness, this system is flushing away the molecular debris of your waking day. Among the waste products cleared by the glymphatic system is a protein called beta amyloid, which has become one of the most studied molecules in neuroscience. Beta amyloid naturally accumulates in the brain during waking hours as a byproduct of normal neural activity. In healthy individuals, sleep clears it efficiently. But when sleep is chronically disrupted, beta amyloid builds up, forming the plaques that are associated with cognitive decline and neurodegenerative conditions. This single fact underscores just how critical sleep is to the long-term health of your brain. The act of sleeping is not passive. It is an active, essential cleansing process. By choosing rest tonight, you are choosing to protect the very tissue that allows you to think, to feel, and to remember. There is a concept in neuroscience known as the critical period, a window of time during early development when the brain is extraordinarily sensitive to environmental input. During these periods, which occur at different times for different abilities, the brain can be shaped with remarkable ease. Vision, language, emotional attachment, all of these capacities are sculpted during their respective critical periods. For a long time, scientists believed that once a critical period closed, the plasticity it enabled was gone forever. But recent research has revealed something far more hopeful. Under certain conditions, including deep sleep, meditation, and enriched learning environments, elements of critical period plasticity can be reopened. Your brain retains, even in adulthood, the latent potential to learn with the depth and flexibility of a child. The idea that adult brains can recapture some of the openness of youth leads us to one of the most poetic aspects of neuroplasticity. Every night when you sleep, your brain enters a state that shares certain electrochemical signatures with the developing brain of an infant. The same growth factors surge. Similar patterns of gene expression activate. The balance between excitation and inhibition shifts in ways that favor the formation of new connections. In a very real sense, sleep returns your brain to a younger version of itself, not permanently, but long enough for deep structural changes to take root. You do not need to travel backward in time to access the plasticity of youth. You simply need to close your eyes and let the ancient rhythms of sleep carry you there. Let us turn now to the remarkable phenomenon known as cross-modal plasticity, the brain's ability to repurpose regions that were originally designed for one sense to serve another. In individuals who are born blind, the visual cortex does not simply go dark. Instead, it is colonized by other senses. It begins to process touch, sound, and even language with extraordinary precision. This repurposing demonstrates that the brain's regions are not defined solely by their original function, but by the input they receive. The architecture is flexible. The blueprint is a suggestion, not a command. And this flexibility is not limited to dramatic cases of sensory loss. In every brain, including yours, regions are constantly negotiating their boundaries, expanding when demanded and contracting when neglected. The plasticity of the motor cortex offers one of the most vivid illustrations of how experience physically reshapes the brain. Studies of professional musicians have shown that the regions of their motor cortex devoted to the fingers of their playing hand are significantly enlarged compared to those of non-musicians. This expansion is not genetic. It is earned, built note by note, practice session by practice session, over years of dedicated repetition. But here is the detail that matters most for tonight. Much of this cortical reorganization is consolidated during sleep. The hours after practice, when the musician rests and the conscious mind releases its grip, are when the brain does its deepest work of integration. Sleep is not the absence of practice. It is the completion of practice. Consider the experience of learning a new language. In the beginning, every sentence requires enormous conscious effort. You must search for vocabulary, assemble grammar, and translate mentally before you can produce a single phrase. But over time, something shifts. The effort decreases. The words begin to arrive on their own. This transition from effortful to automatic processing reflects a physical change in your brain. The circuits involved have been strengthened through repetition, insulated with myelin, and pruned of inefficient detours. Fluency is not a state of knowing more. It is a state of having built smoother, faster, more direct neural highways. And like all construction in the brain, the most important engineering work happens at night, in the silence between one day's practice and the next. There is a phenomenon that sleep researchers call sleep-dependent memory enhancement, and it reveals something almost magical about the relationship between rest and learning. In numerous experiments, subjects who learned a new task and then slept performed significantly better on that task the next day than subjects who spent the same number of waking hours without sleep. The improvement was not simply a matter of being better rested. The sleeping brain had actively refined the memory trace, smoothing out errors, strengthening correct patterns, and integrating the new skill with existing knowledge. You do not learn and then sleep. You learn, and then sleep completes the learning. The two processes are inseparable halves of a single arc. As this first passage of our journey draws toward a gentle pause, consider one final truth that ties everything together. Your brain is not a machine that wears down with use. It is a living system that grows in response to challenge, that heals in response to rest, and that rebuilds itself every single night with a patience and precision that no human technology has ever matched. The neurons reaching out in the dark, the myelin wrapping itself around your fastest thoughts, the glymphatic tide washing through your sleeping mind, all of these processes are unfolding inside you right now. You do not need to direct them. You do not need to understand them fully. You only need to do exactly what you are doing. Breathe slowly, let your thoughts soften, and trust that the garden of your mind knows how to tend itself. As you settle deeper into stillness, your brain is entering a phase of activity that would have astonished scientists just a few decades ago. Far from shutting down, your sleeping brain is launching one of the most intricate maintenance operations in all of biology. Deep beneath the cortex, in spaces so small they are measured in millionths of a meter, a network of channels is widening. The glial cells that spend the day pressed tightly against your neurons are beginning to shrink, pulling back like curtains being drawn from a window. As they contract, they open pathways that were nearly invisible during waking hours. These channels will soon be flooded with cerebrospinal fluid, a clear, gentle liquid that carries with it the power to wash your brain clean. This is the beginning of the glymphatic system's nightly work, and it has already started inside you. The glymphatic system was not discovered until 2013, which means that for the entire history of medicine before that year, humanity had no idea that the brain possessed its own dedicated cleaning network. The discovery was made by a team studying the brains of sleeping mice, and what they found was extraordinary. During deep sleep, the interstitial spaces between neurons expanded by as much as 60%, allowing cerebrospinal fluid to rush through in powerful, rhythmic waves. This fluid carried away metabolic waste that had accumulated during the day, including proteins, cellular debris, and molecular fragments that would otherwise interfere with healthy neural function. The brain, it turned out, had been solving its own waste management problem every single night, in silence, without anyone knowing. Among the most significant substances cleared by this nightly flushing is beta amyloid, a protein that has become central to our understanding of cognitive health. During your waking hours, beta amyloid is produced as a natural byproduct of neural activity. In small quantities, it is harmless, but when it accumulates, it begins to form sticky plaques that interfere with synaptic communication, gradually clouding the precision of thought and memory. Sleep is your brain's primary defense against this accumulation. Each cycle of deep sleep sends another wave of cerebrospinal fluid through the neural landscape, dissolving and carrying away the beta amyloid that gathered during the day. The simple act of sleeping tonight is actively protecting the long-term clarity of your mind. There is another waste product that the glymphatic system targets with quiet efficiency, and that is tau protein. In its healthy form, tau helps stabilize the internal scaffolding of neurons, maintaining the structure that allows electrical signals to travel smoothly along axons. But when tau becomes misfolded or accumulates in excess, it can form tangles inside nerve cells, disrupting their function and eventually leading to their death. Sleep-dependent clearance of tau is one of the brain's most essential housekeeping tasks. Each night, as the glymphatic channels open and the cerebrospinal fluid flows, excess tau is swept away before it can do lasting harm. You are not simply resting, you are protecting the structural integrity of every neuron that holds your memories and your sense of self. The waves of cerebrospinal fluid that move through your brain during sleep do not flow randomly. They pulse in rhythmic patterns that are synchronized with your brain's own electrical activity. During deep, slow-wave sleep, as long, rolling oscillations sweep across the cortex, the blood flow in your brain momentarily decreases. And in the space created by that brief withdrawal, a wave of cerebrospinal fluid rushes in. This coupling between neural rhythms and fluid dynamics is one of the most elegant discoveries in modern neuroscience. Your brainwaves are not merely electrical phenomena, they are physical forces that drive the cleansing tide through your neural tissue. The slow, deep rhythms you are beginning to approach right now are the very engine of your brain's self-purification. As the glymphatic system tends to the physical landscape of your brain, another process is unfolding in parallel, one that concerns not waste removal, but the preservation of everything meaningful you experience today. Memory consolidation is the name neuroscience gives to the transformation of fragile, temporary impressions into durable, lasting knowledge. During the day, your experiences were encoded as patterns of neural activity in the hippocampus, that seahorse-shaped structure nestled deep in each temporal lobe. But the hippocampus is not designed for permanent storage. It is a staging area, a temporary holding room where today's events wait for the night shift to begin. And now, as you drift closer to sleep, the transfer is about to start. The mechanism by which the hippocampus transfers memories to the neocortex is one of the most fascinating processes in all of brain science. During slow-wave sleep, the hippocampus replays the day's experiences in compressed bursts of activity called sharp-wave ripples. These ripples last only fractions of a second, but they contain encoded representations of entire experiences: a conversation, a face, a feeling, a place. Each ripple sends its encoded pattern outward to the neocortex, where it is received and gradually integrated into the vast web of your existing knowledge. Night after night, ripple after ripple, your memories are moved from their temporary home to their permanent one. The process is patient and thorough, and it requires nothing from you except the willingness to sleep. What makes this memory transfer so remarkable is that it is not a simple copying process. The brain does not merely duplicate a memory and store it in a new location. Instead, during consolidation, the memory is transformed. Details that are irrelevant are stripped away. Connections to existing knowledge are strengthened. The emotional tone of the memory may be adjusted. What emerges in the neocortex is not an exact replica of the original experience, but an abstracted, refined version, a version that is more useful, more integrated, and more stable than the raw impression that entered the hippocampus during the day. Sleep does not just save your memories, it improves them, distilling the essence of experience into a form your brain can carry efficiently for years. There is a theory in neuroscience that addresses one of the deepest puzzles about why sleep is necessary, and it is called the synaptic homeostasis hypothesis. Proposed by Giulio Tononi and Chiara Cirelli, this theory suggests that during waking hours, as you learn and experience and absorb information, the overall strength of your synaptic connections steadily increases. Every new thing you notice, every interaction, every thought adds a small increment of synaptic weight. By the end of the day, the total synaptic load has grown so large that it threatens the brain's efficiency and its energy balance. Sleep, according to this theory, is the process by which the brain scales everything back down, selectively weakening synapses to restore a sustainable baseline. Rest is not idleness, it is recalibration. The beauty of synaptic homeostasis lies in its selectivity. Sleep does not weaken all synapses equally. The connections that were most strongly reinforced during the day, the ones associated with meaningful learning and important experiences, are relatively preserved. It is the weaker, less significant connections, the neural noise accumulated through hours of passive exposure and routine, that are preferentially scaled down. This selective downscaling is what allows you to wake up feeling mentally clear rather than overwhelmed. The brain has not erased anything important. It has simply lowered the background noise, increasing the signal-to-noise ratio so that the knowledge and memories that truly matter stand out with greater clarity against a quieter neural landscape. Slow-wave sleep is the primary phase during which synaptic downscaling occurs, and its electrical signature is unmistakable. Great, synchronized waves of activity roll across the cortex, rising and falling with a rhythm that is slower and deeper than anything the waking brain produces. During the rising phase of each wave, millions of neurons fire together in a coordinated burst. During the falling phase, they fall silent simultaneously. This alternation between firing and silence is not random. It is the mechanism by which the brain tests and adjusts its own connections, strengthening those that respond reliably and weakening those that do not. Each slow wave is a question the brain poses to itself, and the pattern of responses it receives determines which synapses will survive the night. As the brain moves through its cycles of sleep, it eventually enters the phase known as rapid eye movement, and here a different kind of neural work begins. REM sleep is when the brain processes the emotional content of your experiences. During this phase, the stress-related neurochemical norepinephrine is almost entirely absent from the brain, creating a unique chemical environment in which memories can be reactivated and reviewed without triggering the full emotional response that accompanied them originally. This is why REM sleep has been described as overnight therapy. The brain replays difficult or distressing experiences, but it does so in a chemically safe space, allowing the factual content of the memory to be preserved while the raw emotional charge is gradually dissolved. The therapeutic function of REM sleep is not a metaphor. It has been measured in laboratories around the world. Subjects who were shown emotionally disturbing images and then allowed a full night of sleep, rich in REM cycles, showed significantly reduced emotional reactivity to those same images the next day. Their memory of the images remained intact, but the visceral sting, the racing heart, the tightness in the chest had faded. Subjects who were kept awake for the same period, or whose REM sleep was selectively disrupted, showed no such reduction. The emotional pain remained as fresh as if it had just occurred. REM sleep does not erase painful memories. It carefully removes their sharp edges, allowing you to remember without being wounded. Dreams, those vivid and often bewildering narratives that emerge during REM sleep, serve a purpose that extends far beyond emotional processing. One of the most compelling theories in modern sleep science proposes that dreaming is a form of simulation. Your brain, freed from the constraints of physical reality and sensory input, creates elaborate scenarios in which you can practice responses to social challenges, threats, and novel situations. These dream simulations activate many of the same neural circuits that would be engaged during real-world experience, effectively training your brain without any of the risks. The predator you outran in a dream, the conversation you navigated, the problem you solved, all of these leave traces in your neural architecture, strengthening the pathways you would need if similar situations arose in waking life. The simulation theory of dreaming helps explain why dream content so often involves themes of pursuit, conflict, and problem-solving. Your brain is not tormenting you with anxiety-driven narratives. It is running drills. Just as a pilot trains in a flight simulator before facing real turbulence, your sleeping brain rehearses challenging scenarios in the safe theater of dreams. The neural pathways activated during these rehearsals are physically strengthened through the same mechanisms of synaptic plasticity that operate during waking learning. This means that your dreams, even the strange ones, even the uncomfortable ones, are contributing to your resilience and your readiness. When you wake tomorrow, you will be fractionally better prepared for the world, and you will have your dreams to thank. There is a particular structure in the brain that plays a central role in the emotional landscape of your dreams, and that is the amygdala. This small, almond-shaped cluster of neurons is your brain's alarm system, the region most responsible for detecting threats and generating the feeling of fear. During REM sleep, the amygdala is highly active, which is why dreams so often carry an emotional intensity that seems disproportionate to their content. But this heightened activation is not a malfunction. It is part of the brain's strategy for processing and ultimately weakening the emotional associations that accumulated during the day. By reactivating fear circuits in the absence of real danger and without the stress chemical norepinephrine, the brain is gently desensitizing itself, teaching its own alarm system to be more accurate and less reactive. While the amygdala processes fear in the dreaming brain, the prefrontal cortex, the region responsible for rational thought and executive control, is significantly quieted during REM sleep. This is why dreams often lack logical coherence, why you accept impossible scenarios without question, and why the passage of time feels distorted in the dream state. But this prefrontal silence is not a flaw. It is a feature. By reducing the influence of the logical, censoring mind, the brain allows itself to make connections between memories and ideas that the waking mind would never permit. This is the neurological basis of creative insight during sleep. The associations that seem absurd in a dream may, upon waking, reveal connections that are genuinely novel and useful. Throughout the night, your brain does not remain in a single state. It cycles through a carefully orchestrated sequence of sleep stages, each serving a distinct function. A typical cycle lasts approximately 90 minutes and moves from light sleep through deep, slow-wave sleep and then into REM before the pattern begins again. The composition of these cycles shifts as the night progresses. In the early hours, deep, slow-wave sleep dominates, prioritizing physical restoration and the consolidation of declarative memories. As dawn approaches, REM periods grow longer and more vivid, favoring emotional processing and creative integration. This architecture is not random. It is a precisely timed program that ensures every type of neural maintenance receives its allotted time and attention. The transition between sleep stages is governed by an elegant interplay of neurotransmitters, each one rising and falling like instruments in a symphony that plays throughout the night. Serotonin and norepinephrine, which keep you alert and focused during the day, gradually diminish as sleep onset approaches. Gamma-aminobutyric acid, known as GABA, rises to inhibit waking circuits and invite the brain into deeper states. Acetylcholine surges during REM sleep, fueling the vivid imagery of dreams while the body remains paralyzed. And melatonin, released by the pineal gland in response to darkness, serves as the conductor of this entire ensemble, signaling to every system in your body that it is time to begin the nightly work of restoration. These chemicals are flowing through you right now, gently guiding you deeper. There is a remarkable phenomenon that occurs at the boundary between waking and sleep, in that liminal space where consciousness begins to loosen its grip. It is called the hypnagogic state, and it is characterized by fleeting images, disconnected thoughts, and a sensation of gentle falling. Neuroscientists have discovered that during this transition, the brain exhibits a unique pattern of activity that combines elements of both waking and sleeping states. The default mode network, which governs mind-wandering and self-reflection, becomes unusually active, while the executive control networks that normally filter and organize your thoughts begin to relax. This creates a brief window of extraordinary associative freedom, a moment when the mind can drift between ideas with a fluidity that is available at no other time. Many creative breakthroughs have emerged from this threshold state. The default mode network itself is one of the most fascinating discoveries in modern neuroscience. This interconnected set of brain regions activates not when you are focused on a task, but when your mind is wandering, daydreaming, or reflecting on yourself and your place in the world. During sleep, the default mode network does not shut down. It continues to operate, weaving together the threads of your experiences, testing connections between distant memories, and maintaining the coherent narrative of your identity. In a very real sense, your sense of self is maintained and updated during sleep by this quietly industrious network. The person you feel yourself to be when you wake tomorrow will have been subtly refined and reinforced by processes that unfolded entirely beyond your conscious awareness. As your brain moves through its nightly cycles, it also performs a kind of physical maintenance on its own cellular infrastructure that is rarely discussed but deeply important. The neurons and glial cells that make up your brain tissue require constant repair. Cellular membranes must be restored. Damaged proteins must be identified and replaced. Mitochondria, the tiny energy-producing organelles within each cell, must be replenished. DNA itself must be inspected for errors and repaired where damage has occurred. Research has shown that the genes responsible for these repair processes are preferentially activated during sleep. Your brain literally turns on its maintenance machinery when you close your eyes, attending to 1,000 microscopic tasks that keep each cell functioning at its best. The repair of DNA during sleep deserves particular attention because the integrity of your genetic material is fundamental to the health of every neuron you possess. During waking hours, normal neural activity generates oxidative stress, producing reactive molecules that can damage the delicate strands of DNA within your cells. This damage accumulates throughout the day, and if left unrepaired, it can lead to errors in gene expression and gradual cellular dysfunction. Studies have shown that sleep activates specific DNA repair enzymes that work through the night to correct these errors. This is not a minor housekeeping task. It is an essential safeguard against the gradual degradation of the very code that instructs your cells how to function. Sleep is, in this sense, the guardian of your genome. There is one more dimension of the brain's nocturnal activity that ties together everything we have explored in this passage, and that is the role of sleep spindles. These are brief bursts of oscillatory brain activity that occur primarily during the lighter stages of sleep, lasting only 1 to 2 seconds each, but occurring hundreds of times throughout the night. Sleep spindles are generated by the thalamus, the brain's central relay station, and they serve multiple functions simultaneously. They help block external sensory input, protecting your sleep from disruption. They facilitate the transfer of information from the hippocampus to the neocortex, and they have been correlated with measures of learning ability and cognitive performance. Each spindle is a tiny act of neural coordination, a fleeting rhythm that contributes to the vast, silent orchestra of your sleeping brain. Let this passage close as gently as it began. The systems you have just learnt about, the glymphatic channels flushing toxins from your tissues, the hippocampal ripples carrying today's experiences into permanent storage, the slow waves scaling down your synapses to restore clarity, the REM cycles softening the emotional edges of your memories, the dream simulations strengthening your readiness for tomorrow. All of these are not distant scientific abstractions. They are happening inside you right now. They are the night shift of your own extraordinary brain, working with a precision and devotion that asks nothing of you in return except this: that you lie still, that you breathe slowly, that you allow the ancient architecture of sleep to do what it has done for every human brain that has ever existed. Let it work. You are in the most capable hands there are, your own. There is a truth about fear that neuroscience has only recently been able to fully articulate, and it is one of the most liberating discoveries ever made about the human brain. Fear is not permanent. The neural circuits that sustain a phobia, a trauma response, or a deep-seated anxiety are not carved into stone. They are maintained by synaptic connections, and synaptic connections can be weakened. The process by which this happens is called extinction learning, and it does not require you to forget the thing that frightened you. Instead, your brain builds a new pathway, one that carries the message that the feared stimulus is no longer dangerous. Over time, with repeated safe exposure, this new pathway grows stronger than the old one. The fear does not disappear from your brain. It is simply overwritten by something more powerful: the knowledge that you survived. Extinction learning is not an abstract concept studied only in laboratories. It is the foundation of some of the most effective therapeutic approaches in modern psychology. When a person with a phobia gradually confronts the object of their fear in a controlled, safe environment, what is happening at the neural level is the construction of a competing memory. The original fear circuit still exists, but each safe encounter deposits a new layer of synaptic strength over the alternative pathway. Eventually, the brain's default response to the trigger shifts from alarm to calm. This process is significantly enhanced by sleep. Studies have shown that extinction memories consolidate more effectively after a full night of rest, meaning that the healing work you do during the day is sealed and strengthened by the sleep that follows. The brain's ability to rewrite its fear responses reveals something profound about the nature of trauma. A traumatic experience creates an exceptionally strong neural circuit because the amygdala, flooded with stress hormones at the time of the event, encodes the memory with an intensity that ordinary experiences never receive. This is why traumatic memories feel so vivid, so present, so resistant to the passage of time. But the very plasticity that allowed the trauma to be encoded so deeply is the same plasticity that allows it to be gradually softened. The brain that was shaped by pain possesses the same mechanisms needed to reshape itself toward peace. Healing is not a matter of willpower or positive thinking. It is a physical process of neural reorganization, and it is happening in brains all over the world, including yours, every single day. One of the most remarkable demonstrations of the brain's capacity for emotional reorganization comes from research into mindfulness meditation. Studies using brain imaging have shown that individuals who practice mindfulness consistently over a period of weeks or months undergo measurable structural changes in their brains. The prefrontal cortex, the region responsible for rational thought, emotional regulation, and conscious decision-making, physically thickens. Its neural connections become denser, its gray matter volume increases. At the same time, the amygdala, the brain's fear and threat detection center, begins to shrink. Its reactivity decreases. The balance of power between the impulsive, anxious parts of the brain and the calm, deliberate parts shifts in favor of clarity and composure. Mindfulness does not just feel calming, it physically rebuilds the architecture of emotional control. The structural changes produced by mindfulness are not limited to the prefrontal cortex and the amygdala. Research has also documented increased connectivity between the prefrontal regions and the insula, a brain area involved in body awareness and empathic understanding. This enhanced connection means that mindful individuals become better at recognizing their own emotional states and responding to them with intention rather than reflex. They also become more attuned to the emotions of others. The practice of sitting quietly and observing your own breath, your own thoughts, your own sensations without judgment is simultaneously training the brain to be more present, more compassionate, and more resilient. Each session of stillness is a session of neural construction, and the architecture being built is one of profound emotional intelligence. Consider now the effect that a simple shift in attention can have on the physical structure of your brain. When you deliberately focus on something you are grateful for, a specific cascade of neural events is set in motion. The prefrontal cortex activates as you direct your attention. The anterior cingulate cortex, involved in emotional awareness, lights up as you register the positive feeling. And most importantly, the ventral tegmental area and the nucleus accumbens, the core components of the brain's reward system, release dopamine, the neurotransmitter associated with pleasure, motivation, and satisfaction. This is not a vague spiritual claim. Gratitude physically stimulates the same reward circuits that respond to food, music, and human connection. By practicing gratitude, you are literally training your brain to find more joy in the life you already have. The neuroplastic effects of gratitude do not require grand gestures or extraordinary circumstances. Research has shown that even brief, daily practices, such as mentally noting 3 things you appreciated about your day, produce measurable changes in brain activity over time. The neural pathways associated with positive emotional processing become stronger and more readily activated. The threshold for experiencing satisfaction lowers, meaning that smaller pleasures begin to register with greater intensity. Meanwhile, the pathways associated with rumination and negativity, while never fully erased, become less dominant. The brain, always responsive to where attention is directed, gradually reshapes its default emotional landscape. You are not born with a fixed capacity for happiness. You build it, synapse by synapse, thought by thought, night by restful night. The brain's reward system, so responsive to gratitude and positive attention, is also deeply influenced by social connection. Human beings are fundamentally social creatures, and the brain reflects this in its architecture. When you engage in a warm conversation, when you share laughter with someone you trust, when you experience the simple comfort of being understood, your brain releases not only dopamine but also oxytocin, a neuropeptide that promotes bonding, trust, and a sense of safety. Oxytocin does more than create a pleasant feeling. It actively modulates the amygdala, reducing its reactivity and lowering the baseline level of anxiety in your nervous system. Each meaningful social interaction is a small act of neural healing, a moment in which your brain chemistry shifts toward peace and away from vigilance. The influence of social connection on neuroplasticity extends beyond chemistry into structure. Studies of individuals with rich, supportive social networks have revealed differences in brain anatomy compared to those who are more isolated. The regions involved in social cognition, including the temporoparietal junction and the medial prefrontal cortex, tend to show greater gray matter volume in people with strong social bonds. The mirror neuron system, which allows you to understand and empathize with the actions and emotions of others, becomes more refined and responsive through regular social engagement. Loneliness, by contrast, has been shown to increase amygdala reactivity and reduce prefrontal efficiency. Your relationships are not separate from your brain health. They are one of the most powerful forces shaping its physical structure. Empathy, that quiet ability to feel what another person feels, is itself a product of neuroplasticity. You were not born with a fixed capacity for empathy. The neural circuits that support it, particularly the anterior insula and the anterior cingulate cortex, develop and strengthen through experience. Every time you listen to someone with genuine attention, every time you imagine yourself in another person's circumstances, you are exercising these circuits. And like any neural pathway that is repeatedly activated, they grow stronger with use. This means that empathy is not merely a personality trait. It is a skill, a neural habit that can be cultivated deliberately. And as it grows, it changes not only how you relate to others, but how your brain processes the entire emotional landscape of your life. Let us turn now to one of the most common and personal expressions of neuroplasticity, the formation and transformation of habits. Every habit you possess, from the way you reach for your phone in the morning to the way you respond to stress, is encoded as a neural circuit in a region called the basal ganglia. This cluster of structures deep in the brain is responsible for automating repeated behaviors, allowing them to run with minimal conscious effort. Once a habit circuit is established, it becomes remarkably efficient, requiring far less energy than a consciously directed action. But here is the crucial detail that shapes our understanding of change. Old habit circuits are almost never fully deleted. They remain in the basal ganglia like faded paths through a forest. What changes is which path the brain chooses to follow. The persistence of old habit circuits explains why breaking a habit can feel so difficult, and why relapse is so common. The old pathway is still there, ready to be reactivated by the right trigger. But neuroplasticity offers a way forward that does not require erasing the past. Instead of trying to destroy the old circuit, you build a new one. Through deliberate repetition of the desired behavior, you lay down a new neural pathway that runs parallel to the old one. Each time you choose the new behavior, the new circuit grows a little stronger, a little more myelinated, a little more automatic. Eventually, the new pathway becomes the brain's default response. The old one does not vanish, but it fades into disuse, overgrown and quiet, like a road that no one travels anymore. The architecture of a habit loop is beautifully simple. It consists of three components: a cue, which triggers the behavior, a routine, which is the behavior itself, and a reward, which reinforces the circuit and makes repetition more likely. Understanding this loop is the key to consciously directing your own neuroplasticity. If you want to build a new habit, you do not need extraordinary discipline. You need a consistent cue, a clear routine, and a reward that your brain's dopamine system can recognize. Over time, the repetition of this loop will physically encode the behavior into the basal ganglia, transforming what once required conscious effort into something that feels as natural and effortless as breathing. You have already built thousands of habits this way. You can build new ones with the same machinery. The role of dopamine in habit formation deserves special attention because it illuminates why certain behaviors become compulsive while others never take root. Dopamine is not simply a pleasure chemical. It is a prediction chemical. It surges not when you receive a reward, but when you anticipate one. This anticipatory signal is what drives you to repeat a behavior, what makes the cue so powerful and the routine so automatic. When you build a healthy habit, you are training your dopamine system to associate the cue with a positive outcome, creating a self-reinforcing cycle that grows stronger with every repetition. This is the same mechanism that underlies addiction, but directed toward growth rather than destruction. The chemistry is identical. The direction is a choice, and it is a choice you can make again and again. Sleep plays a critical role in the consolidation of new habit circuits, just as it does in the consolidation of memories and skills. Research has demonstrated that the neural patterns associated with newly practiced behaviors are replayed during sleep, particularly during slow-wave sleep, strengthening the synaptic connections that will make the behavior more automatic upon waking. This means that if you are working to build a new habit, the night that follows your practice is as important as the practice itself. Each sleep cycle is an opportunity for the brain to reinforce the circuit you are building, to add another layer of myelin, to prune away the competing connections that might divert you back to the old pattern. Rest is not a pause in the process of change. It is the process of change. There is a quality of the mind that neuroscience has come to recognize as one of the most important predictors of lifelong cognitive health, and it is called cognitive flexibility. This is the brain's ability to shift between different concepts, perspectives, or strategies in response to changing circumstances. A cognitively flexible mind can release one train of thought and adopt another without becoming stuck or rigid. It can hold multiple viewpoints simultaneously without confusion. It can adapt to novel situations with creative, fluid responses rather than defaulting to habitual patterns. Cognitive flexibility is governed primarily by the prefrontal cortex, and like every capacity of the brain, it is subject to neuroplasticity. It can be strengthened through practice, and it can be diminished through neglect. The cultivation of cognitive flexibility is one of the most effective ways to keep the brain resilient as it ages. Activities that require you to switch between tasks, to learn new skills, to engage with unfamiliar ideas, or to solve problems that have no single correct answer, all stimulate the prefrontal circuits that underlie flexibility. Even something as simple as taking a different route home, cooking a meal from an unfamiliar cuisine, or engaging in a conversation with someone whose perspective differs from your own, creates a small but meaningful demand on your brain's flexibility systems. Each demand is a stimulus, and each stimulus is an invitation for the brain to strengthen the connections that keep it adaptable. Rigidity is not an inevitable consequence of aging. It is the consequence of a brain that has stopped being challenged. The relationship between cognitive flexibility and emotional well-being is deeper than most people realize. When the brain becomes rigid in its thinking patterns, it also becomes rigid in its emotional responses. A mind that cannot shift perspectives cognitively is a mind that struggles to reframe emotional experiences. It gets trapped in loops of rumination, replaying the same distressing thoughts because it lacks the neural agility to redirect its own attention. By contrast, a flexible brain can recognize a negative thought pattern, disengage from it, and redirect its focus toward more constructive territory. This is not suppression. It is cognitive agility, and it is built through the same mechanisms of repetition, reinforcement, and sleep-dependent consolidation that govern all forms of neuroplastic change. There is a concept in psychology known as post-traumatic growth, and it represents one of the most hopeful expressions of neuroplasticity in the entire scientific literature. Post-traumatic growth refers to the positive psychological change that can emerge in the aftermath of a deeply challenging life experience. It is not the absence of suffering. It is the transformation that suffering can catalyze when the brain is given the right conditions for healing. Individuals who experience post-traumatic growth often report a deeper appreciation for life, stronger relationships, a greater sense of personal strength, and a richer spiritual or philosophical understanding. These changes are not purely psychological. They correspond to measurable shifts in brain activity and structure, particularly in the prefrontal cortex and the networks involved in meaning-making and self-reflection. The brain's capacity for post-traumatic growth reminds us that neuroplasticity is not a neutral force. It does not simply respond to experience. It responds to the meaning we assign to experience. Two people can undergo the same hardship and emerge with profoundly different neural architectures, depending on how their brains process and integrate what happened. This is not about blame or about the false idea that attitude alone determines outcome. It is about the scientifically documented reality that the stories we tell ourselves about our experiences physically shape the circuits that process those experiences. The narrative you construct about your own life is not separate from your brain. It is part of your brain, encoded in synaptic patterns that grow stronger or weaker depending on how often and how deeply you engage with them. Self-compassion, the practice of treating yourself with the same kindness and understanding you would offer a close friend, has been shown to produce neuroplastic changes that mirror those of mindfulness and gratitude. When you respond to your own mistakes or suffering with warmth rather than harsh self-criticism, you activate the brain's caregiving system, a network that includes the ventromedial prefrontal cortex and the insula. This network releases oxytocin and endorphins, reducing the activity of the amygdala and the stress-related cortisol response. Over time, the habitual practice of self-compassion physically strengthens the neural circuits of emotional safety and weakens the circuits of self-punishment. You are not indulging yourself by being kind to your own mind. You are rewiring it toward resilience. The brain's response to music offers a vivid and deeply personal example of neuroplastic change in action. When you listen to music that moves you, nearly every region of your brain activates in concert. The auditory cortex processes the sound. The motor cortex responds to rhythm. The limbic system generates emotion. The prefrontal cortex engages with structure and anticipation. And the reward system floods with dopamine at moments of musical surprise or resolution. This whole brain activation is one of the reasons music is so effective at inducing relaxation and promoting sleep. It does not target a single neural pathway. It bathes the entire brain in coordinated activity, and that coordination itself is a form of neural exercise that strengthens the connections between regions and promotes integration across the whole mind. There is a principle in neuroscience that describes the brain's remarkable ability to compensate for lost function by recruiting neighboring regions, and it is known as vicariance. When a specific brain area is damaged through injury or disease, surrounding regions can gradually take over some of its responsibilities. This process is slow and imperfect, but it demonstrates the extraordinary depth of the brain's plastic potential. Vicariance is driven by the same Hebbian mechanisms that govern all learning. As the remaining neurons are repeatedly called upon to perform the lost function, their connections strengthen, their dendrites extend, and new synaptic partnerships form. The brain does not accept loss passively. It reorganizes, adapts, and rebuilds, not to the original blueprint, but to a new one that accommodates the changed landscape. The phenomenon of vicariance is most dramatic in cases of early brain injury, where the developing brain's heightened plasticity allows for remarkable recovery. But it is not limited to the young. Adult brains, too, demonstrate the capacity to reorganize after damage, albeit more slowly and with more deliberate effort. Rehabilitation programs that harness the principles of neuroplasticity using repetitive practice, enriched sensory environments, and carefully graded challenges can facilitate recovery that was once considered impossible. Each repetition is a signal to the brain that this function matters, that these neurons must be recruited, that these connections must be built. The patience required is immense, but the biological machinery that makes recovery possible is already present in every human brain, waiting to be activated. As this section of our journey comes to a close, let yourself absorb the central truth that has woven through every paragraph you have heard. You are not a finished product. You are not defined by your past fears, your old habits, your most painful memories, or the version of yourself that existed yesterday. Your brain is a living, breathing organ of change, capable of weakening the circuits that no longer serve you and strengthening the ones that carry you toward the person you are becoming. This process does not require perfection. It does not require speed. It requires only repetition, patience, and the one thing you are giving it right now: rest. Sleep is where the scaffolding of your new self is quietly assembled, beam by beam, synapse by synapse, in the gentle dark behind your closed eyes. Trust the process. Trust your brain. It already knows what to do. There is a concept in neuroscience that offers one of the most reassuring truths about growing older, and it is called cognitive reserve. Throughout your life, every book you have read, every language you have studied, every conversation that challenged your assumptions, every problem you solved in a way you had never tried before, all of these experiences have been quietly building a reserve of neural complexity within your brain. This reserve does not prevent the physical changes that come with age, but it provides an extraordinary buffer against them. A brain rich in cognitive reserve has so many alternative pathways, so many redundant connections, so many deeply myelinated circuits, that when some inevitably weaken or fail, others are already in place to carry the signal forward. Learning is not just enrichment. It is a form of long-term neural insurance. The evidence for cognitive reserve comes from some of the most compelling studies in the history of brain science. Researchers examining the brains of individuals who had shown no cognitive decline during their lifetimes have sometimes found, upon autopsy, significant physical signs of neurodegeneration, plaques, tangles, and tissue loss that would typically be associated with severe impairment. Yet these individuals had continued to think clearly, to remember vividly, and to engage fully with the world until the very end. The difference was not the absence of damage. It was the presence of such a vast and interconnected neural network that the damage could be absorbed without visible effect. Their lifelong habits of curiosity and intellectual engagement had built a brain that could sustain losses and still function with grace. This leads us to a remarkable group of individuals whom researchers have termed super-agers. These are people in their 70s, 80s, and beyond, whose cognitive performance, particularly in memory and attention, matches or even exceeds that of people decades younger. Brain scans of superagers reveal something that initially puzzled scientists. Their cortex, particularly in regions associated with memory and emotional processing, is significantly thicker than that of their age-matched peers. The anterior cingulate cortex, a region involved in sustained attention and emotional resilience, is especially well preserved. Superagers are not genetically privileged anomalies. They tend to share common traits: a commitment to challenging mental activity, strong social bonds, physical exercise, and a willingness to endure the discomfort of learning new things rather than retreating into the familiar. What superagers teach us is that the trajectory of brain aging is not fixed. The assumption that cognitive decline is an inevitable companion of advancing years has been quietly dismantled by decades of research. Plasticity does not have an expiration date. The brain of a 70-year-old who continues to learn, to exercise, to socialize, and to engage with novel challenges is a fundamentally different organ from the brain of a 70-year-old who has withdrawn into routine. The neurons still respond to stimulation. The dendrites still reach out for new connections. Neurogenesis, though slower than in youth, still occurs in the hippocampus. The machinery of change is still present. It is simply waiting for the signal that change is needed, and that signal is always the same: use, challenge, engagement, and rest. Physical exercise deserves its own moment of recognition in the story of brain longevity, because its effects on neuroplasticity are among the most robust and well documented in all of neuroscience. When you move your body, particularly in sustained aerobic activity, your muscles release a cascade of molecules that cross the blood-brain barrier and directly stimulate neural growth. Chief among these is brain-derived neurotrophic factor, BDNF, which promotes the survival of existing neurons, encourages the birth of new ones, and strengthens synaptic connections throughout the brain. Exercise also increases blood flow to the hippocampus, enhances the clearance of metabolic waste, and reduces systemic inflammation that would otherwise erode neural health. A body in motion is a brain in bloom, and this remains true at every stage of life. Now let us explore a state of consciousness that represents one of the most exquisite expressions of a well-connected brain. It is called flow, and you have almost certainly experienced it. Those moments when you become so deeply absorbed in an activity that time seems to dissolve, self-consciousness vanishes, and your actions unfold with an effortless precision that feels almost dreamlike. Neuroscience has begun to understand the brain activity underlying flow, and the findings are extraordinary. During flow states, a phenomenon called transient hypofrontality occurs. The prefrontal cortex, which normally generates your inner critic, your sense of time, your self-monitoring, temporarily quiets. With its filters removed, the brain enters a state of uninhibited processing where creativity, pattern recognition, and motor coordination merge into a single, seamless stream. The neurochemistry of flow is equally remarkable. During these states, the brain releases a potent cocktail of neurochemicals: dopamine for focus and reward, norepinephrine for arousal and attention, endorphins for pain reduction and pleasure, anandamide for lateral thinking and pattern recognition, and serotonin for a deep sense of well-being that lingers long after the flow state has ended. This chemical cascade does not just feel good, it enhances neuroplasticity, making the brain more receptive to new connections and more efficient at consolidating the skills being practiced. Flow is not merely a peak experience. It is a peak state of neural construction, a window during which the brain is simultaneously performing at its highest level and reshaping itself to perform even better in the future. Creativity itself, that mysterious capacity to bring something new into existence, is fundamentally a product of neuroplastic processes. Creative thought requires the brain to combine existing neural patterns in novel ways, to bridge distant regions that do not ordinarily communicate, to find connections that no one has noticed before. This is why creative insights so often arrive not during focused effort, but during moments of relaxation, daydreaming, or the threshold of sleep. When the prefrontal cortex relaxes its executive control, the default mode network is free to wander, testing associations across the vast landscape of stored knowledge. Creativity is not a gift bestowed upon a few. It is an emergent property of a brain that has been given permission to explore without judgment. And that permission is most freely granted in states of rest. The connection between sleep and creativity has been documented across centuries of human achievement. Breakthroughs in science, art, music, and literature have emerged from dreams and from the hypnagogic states between waking and sleeping. This is not coincidence. During REM sleep, the brain's associative networks are maximally active, while the logical constraints of the prefrontal cortex are minimally present. The result is a kind of neural brainstorming session in which the brain tests millions of combinations of ideas, memories, and sensory impressions, most of which are discarded, but some of which survive as genuinely novel insights. When you allow yourself to drift into sleep tonight, you are not leaving your creative work behind. You are handing it to the most inventive version of your brain, the one that works best without you watching. There is a dimension of neuroplasticity that extends beyond the individual brain and into the shared space between minds. When two people engage in deep, attentive conversation, their brain waves begin to synchronize. This phenomenon, called neural coupling, has been measured using brain imaging, and it reveals that communication is not merely an exchange of words. It is a physical alignment of neural activity between two separate brains. The listener's brain begins to mirror the speaker's patterns, sometimes even anticipating them. This synchrony strengthens the social neural networks in both individuals simultaneously. Every meaningful conversation you have is a shared act of neuroplasticity, a moment in which two brains are literally shaping each other through the invisible medium of attention, language, and presence. The brain's capacity for interpersonal synchrony points to something deeper about the nature of neural architecture. Your brain did not evolve in isolation. It evolved within communities, within families, within networks of mutual dependence and shared meaning. The circuits that allow you to understand another person's facial expression, to feel moved by a piece of music, to sense the mood of a room you have just entered. All of these are products of millions of years of social evolution, encoded in neural structures that are exquisitely tuned to the presence of other minds. Your brain is not a solitary organ. It is a social organ, designed to exist in relationship, and it achieves its highest levels of plasticity and integration, not in isolation, but in connection. There is a phenomenon in the study of complex systems that has captured the imagination of scientists and philosophers alike, and it concerns the deep structural similarity between the neural networks of the brain and the large-scale structure of the universe. When astronomers mapped the distribution of galaxies across the observable cosmos, they discovered a vast web of filaments and clusters, with galaxies strung along these filaments like dewdrops on a spider's silk, separated by enormous voids. Neuroscientists, looking at images of neural networks, noticed something haunting. The branching patterns, the clustering, the ratio of matter to empty space, all bore a striking resemblance to the cosmic web. The architecture of your thoughts mirrors the architecture of the cosmos. You carry within your skull a structure that echoes the shape of the universe itself. This resemblance between neurons and galaxies is not merely visual. Mathematical analyses have shown that the networks of the brain and the networks of the cosmos share similar levels of complexity, similar organizational principles, and similar distributions of connectivity. Both systems self-organize through local interactions into structures of breathtaking intricacy. Both balance efficiency with redundancy. Both exhibit the hallmarks of what physicists call a scale-free network, where a few highly connected nodes anchor vast webs of smaller connections. Whether this similarity is a coincidence of mathematics or a reflection of some deeper principle of organization remains an open question. But tonight, as you lie beneath the dark, you can hold this thought gently. The universe that stretches above you and the mind that contemplates it are built on the same elegant blueprint. Consider now the state of consciousness that contemplative traditions have described for thousands of years and that neuroscience is only beginning to understand. It is the experience of ego dissolution, the temporary fading of the boundary between self and world. During deep meditation, during moments of profound awe, and during certain phases of sleep, the default mode network, which maintains your sense of being a separate self, quiets dramatically. When it does, the brain enters a state of heightened global connectivity. Regions that normally operate independently begin to communicate in rich, synchronized patterns. The result is an experience of unity, of boundarylessness, of being part of something far larger than the individual mind. This is not mysticism. It is measurable neural activity, and it represents one of the brain's most integrated and efficient modes of operation. The science of awe, that overwhelming emotion you feel when confronted with something vast and incomprehensible, has revealed its own unique neuroplastic signature. Awe activates the prefrontal cortex while simultaneously quieting the default mode network, creating a state in which the mind is both fully alert and free from self-referential thinking. This combination promotes a sense of humility, connectedness, and openness to new information. Studies have shown that experiences of awe reduce inflammatory markers in the body, lower stress hormones, and increase prosocial behavior. Awe is not simply a pleasant emotion. It is a neurological event that shifts the brain toward greater integration, greater flexibility, and greater openness to change. The universe did not give you the capacity for awe by accident. It gave it to you as a doorway. There is a form of neural oscillation that emerges during states of deep meditation and sustained creative absorption, and it is called gamma wave activity. Gamma waves are the fastest brain waves, oscillating at frequencies above 30 cycles per second, and they are associated with heightened perception, enhanced memory formation, and the binding together of information from different brain regions into a unified conscious experience. Long-term meditators show dramatically elevated levels of gamma activity, even during ordinary waking states, suggesting that their brains have been permanently reorganized toward greater coherence and integration. Gamma waves represent the brain operating at its highest level of coordination, every region contributing its voice to a single, harmonious chorus that transcends the sum of its parts. The brain's highest states of integration share a common feature that is worth pausing to appreciate. In every case, whether it is flow, deep meditation, or the synchronized rhythms of restorative sleep, the brain achieves its peak performance not by working harder, but by working together. The barriers between regions dissolve. The noise of competing signals quiets. The entire organ begins to pulse as a single, unified system, and the experience that accompanies this unity is invariably one of peace, clarity, and a profound sense of rightness. This is not an accident of evolution. It is a design principle. Your brain was built to function as a whole, and the moments when it achieves that wholeness are the moments when you feel most fully alive and most deeply at rest simultaneously. The practice of deep breathing, so often recommended as a pathway to calm, has a neuroplastic dimension that is rarely discussed. Each slow, deliberate breath activates the vagus nerve, the longest cranial nerve in the body, which sends calming signals from the body directly to the brainstem, the amygdala, and the prefrontal cortex. Over time, the repeated stimulation of this pathway strengthens it, lowering the brain's baseline level of arousal and increasing the efficiency of the parasympathetic nervous system. The simple act of breathing slowly is, at the neural level, a form of repetitive training that physically reinforces the circuits of calm. Tonight, each breath you take is a repetition, a small signal to your brain that you are safe, that the world outside can wait, that this moment of stillness is enough. As you descend further towards sleep, your brain is approaching a state that scientists are only beginning to understand in its full depth: deep, dreamless sleep, the phase in which consciousness as you know it entirely recedes, is not an absence. It is a presence of a different kind. During this phase, the brain's activity drops to its most synchronized and most fundamental rhythms. The slow oscillations that sweep across the cortex are not the remnants of waking thought. They are the brain's most elemental voice, the sound it makes when it is no longer speaking to the world, but only to itself. In this state, synaptic homeostasis reaches its deepest expression. The noise of the day is fully cleared. The signal of what truly matters is all that remains. There is something sacred about the threshold you are approaching now, a place where thought begins to thin, where the weight of identity lifts, where the boundary between you and the darkness around you becomes soft and permeable. Neuroscience tells us that in the deepest phases of sleep, the thalamus closes its gates to the outside world, sealing the brain inside a cocoon of self-generated rhythms. Sensory input is blocked. Time loses its meaning. The brain is alone with itself, free to repair, to consolidate, to create, to dissolve, to rebuild. This is not unconsciousness. It is the deepest form of consciousness, turned inward, folded gently upon itself, like a universe contemplating its own existence in perfect silence. You are approaching that silence now, and there is nothing you need to do to earn it. The brain that carried you through today, that processed 1,000 decisions, that felt joy and fatigue and curiosity and doubt, that brain is not asking you for effort. It is asking only for permission. Permission to do what it has done every night since you were born. To dissolve the boundaries of the day. To wash the pathways clean. To reach out with its dendrites into the dark and find new connections that will be waiting for you when the light returns. Let your thoughts grow thin now, thinner than paper, thinner than breath. Let them become transparent until you can see through them to the stillness that has always been beneath. Your neurons are quieting, one by one, like stars appearing in reverse, not vanishing, but softening, dimming into a glow that is gentler than anything the waking world allows. The architecture of your mind is settling into its deepest rhythm. A rhythm older than language, older than memory. A rhythm that your brain shared with the first creatures that ever slept on this ancient, turning world. There is nothing left to learn tonight, nothing left to hold, nothing left to become. The facts have finished their quiet work, each one a seed planted in the garden of your sleeping mind, each one a connection waiting to take root in the rich soil of rest. The glymphatic tide is flowing. The slow waves are rolling across your cortex like weather across an open sea, and somewhere deep inside the hippocampus, today is being gently folded and placed on a shelf alongside every other day you have ever lived, preserved, honored, and released. And so the final truth is the simplest one of all. You were never broken. You were never finished. You were always, in every moment, in every breath, a brain remaking itself in the image of everything it has loved and learned and lost and found again. Sleep now. The universe inside you and the universe above you are made of the same elegant pattern, and tonight they rest together in perfect, boundless silence.